lecture, we are going to learn about some other carbon-based composites. So we have already learnt about CFRPs, carbon fiber reinforced plastics. We also now know about the carbon-carbon composites. But as I had mentioned previously, we also have other materials such as carbon metal or carbon ceramic composites or carbon concrete. So basically, you can keep on changing the matrix and then you can get newer carbon materials. In all cases, one thing that remains valid is that the interface properties are very important. The interface between your additive phase and your matrix phase. So now as we keep on changing the nature and the properties of the matrix, then the interface properties also accordingly change, or the the surface treatment that you need to perform, that also accordingly changes. But in any case, that is very important for the strength of your structure. Now, what I'm going to do here is I'm not going to go into the details of the mechanics of all kinds of structures, because also I may not be an expert in some of these areas. For example, the carbon reinforced concrete. So, however, one thing that we are going to discuss is how to make these materials. So, some manufacturing aspects or some fundamental things about these three types of carbon-based composites. Okay, so let us get already started with the carbon metal composites. So as the name suggests, you have a carbon additive, which again is mostly carbon fiber being the most common additive. So it is carbon fiber mixed inside a metal matrix phase. Okay, so how will that work? What are the things that change? So we often mix these carbon fibers into polymers, resins. Now what we are doing is we are mixing them into metals. So the manufacturing processes, the preparation processes will definitely change slightly. Why? Because the metals have different properties compared to your polymers. Their melting points are different. They have different ductility values. So that is why slight changes in the process will definitely be there. When we say metal matrix, it doesn't have to be an element. It can also be an alloy. It can even be an intermetallic compound. So any metal-based matrix is what we are talking about. In fact, sometimes we have these very high strength or high performance alloys, and if you further add carbon fiber to it, then you can imagine that the strength increases so many folds, and then those materials can become really, whatever is called next generation material and so on. Okay, so yeah, again I mentioned that carbon fiber is the most common additive. Now the metals are, number one, ductile, and then you can also make thin and long sheets out of metal. So you know already these properties of this. They are malleable and they are ductile. Now we had also learned about this ductility property before in one of our previous lectures. So you can see in the stress strain curve, this is your region of the before the fracture, after the material stops behaving as an elastic material, and then you have a certain region of strain, and then you have the fracture. So this region is known as ductile behavior. Now metals have a very large enough region of ductility, measurable, but also in the case of carbon fibers, occasionally you will see some ductility in the case of turbostratic carbon fibers. Anyway, this is something we've already covered before. Mostly carbon fibers do not display ductility. So compared to metals, anyway, that is negligible, if at all. Okay, so this is our matrix phase, and what we have is carbon fiber as additive. Now, why do we need, again, so what is the need for carbon matrix composites, and why couldn't we work with carbon composites, even if we wanted to work at higher temperatures? Well, here the ductility and the ability to make thin sheets becomes important. So if you would like to use the properties of a metal, but at the same time what you want is a slightly stronger material, mechanically stronger material, in that case you can add carbon additives to it. Okay, now at this if you do this, then you will at higher temperatures will also get a better strength from the material. So basically the idea is that metals have very interesting properties. Metals offer a lot of properties that also carbon or ceramics don't offer. So other than the physical properties or the ductility and malleability, you also have good thermal conductivity and good electrical conductivity. So we have actually in all these applications, especially when we talk about composites, we focus on mechanical properties of the material, and we have been ignoring the electrical properties. Because mostly what we are talking about is structures with high strength. But we are often ignoring the electrical properties. We are also thermal properties here and there, they are important, but in the case of metals, thermal electrical properties are often utilized for making a lot of structures, for making a lot of devices. But what happens is that, well, your metal will have a good thermal conductivity, high thermal conductivity, but what it will also have is a high thermal expansion coefficient. What does that mean? That when you heat the material, it will expand. That is something which can be undesired when you want to make structures that need to function at very high temperatures. Because what you need when you say certain material or certain structure is good for high temperature applications, what you basically mean that it does not deform at higher temperatures, or it can withstand thermal shocks. That is unfortunately not the case with metals, or most of the metals. Of course, we do make these high performance alloys and super alloys, but in general, if you want to just improve the, you want to ensure that your metal does not expand so much at higher temperatures, then what you can do is you can add these carbon fiber like materials, because we know this very well that our carbon materials have a low thermal expansion coefficient and they are very good at withstanding the thermal shock. And that is why now you can have good electrical conductivity, so basically the property of the metal, good thermal conductivity, but low thermal expansion coefficient. Okay, so this is why we need these kind of materials. So there is this, what is known as the mismatch of thermal expansion coefficients, and that basically makes your material withstand a lot of thermal stresses. And these kind of structures are also used for making heat sink for various electronic devices, for example. Okay, so now what we want to do is we need to figure out how much carbon fiber should be added. So you know that in the case of CFRPs, it's typically 60%. But in the case of metal matrix composites, it's slightly lower, because often you want to utilize the properties of your metal efficiently. You don't want to, reduce the thermal conductivity of your overall structure or electrical conductivity. So the goal here is to strengthen the metal, utilize the properties of the metal rather than that of the carbon fiber. Carbon fiber here would be typically to provide a low thermal expansion and also mechanical strength to the structure at higher temperatures. Okay, so that is why you will use something like 30 to 50% carbon fiber. Again, mostly carbon fiber. Okay, so there are various metal matrix metals that have been used as matrix materials. For example, aluminum, magnesium. So you can also find various metals in the literature. Okay, now how do we perform the processing? That is important for us. Okay, so now think about the manufacturing techniques that you can use with metals. There are so many of them. In fact, we are rather limited when we work with carbon, when we work with ceramics, but when we are working with metals, then a lot of traditional manufacturing techniques can be used. So if we carefully use the content of carbon fiber, so we do not make it so much, such a high concentration that we lose the, properties of the metal, in that case, well, techniques that are traditionally used with metals can also be used. And again, you will have to think about what kind of composites it's going to be. Is it going to be a short fiber composite, or is it going to be a laminate? The answer is both. We can make both types of composites again using a metal matrix, but the manufacturability slightly differs. So I have divided it into 3 types. Okay, so there is a solid state processing, liquid, so where your metal is liquid, and then there are some deposition techniques as well. So let's talk about them. The first one is solid state processing. Now we talk about powder metallurgy. So powder metallurgy is again good old-fashioned manufacturing process. I had also provided you with a reference in the previous lecture where you can learn about basic manufacturing techniques in case you are not from that background. Okay, what you do is you take carbon fibers, in this particular case chopped fibers or short fibers. They can be vapor grown or they can be spun and then chopped. Okay, you take these fibers and then you perform ball milling. Simple standard ball milling. You mix metal powder and you mix your carbon fiber. And then you perform ball milling. Of course, you will need to optimize ball milling parameters, but well, this is how you mix the two phases, and then you can perform simple powder metallurgical techniques such as die casting. So you can pack now this entire mixture inside a die and then perform the heat treatments for sintering. If you want to go to higher temperatures, that would depend on your metal. If you want to go to very high temperatures, then you have to accordingly choose the material of your die. You can even choose a graphite die. Typically, steel die would work. Okay, so now you perform the heat sintering, and then with that mixture, you can even perform extrusion. And high temperature extrusion, again depending upon the properties of your metal. So again, our carbon fibers will not be affected no matter how high what temperature do you use. So carbon fibers are stable. So then your manufacturing technique will mainly depend upon the matrix material rather than the fiber. So this is number one. Okay, what else? We can do something known as diffusion bonding. So I just told you that we can also use laminates. How do we do that? You know that we can buy these carbon fiber preforms. So preform is basically where you have, it's a woven carbon fiber mat. Of course, it will also contain some resin. You know that because as for lubrication and so on, but not so much. You may have to perform certain surface treatment or sizing if you want to mix it into a metal matrix. But what you can do is you can just simply take these carbon fiber preforms or woven mats, and then you can, so here I have shown it in this picture. Then what you can do is you can have metal sheets, thin sheets, foils of metal. So one foil, then one carbon preform, and then another foil, so sandwich structure that looks like this. Okay, and now what you can do afterwards, you can heat it slightly, but not to very high temperatures. You can heat it and compress it. So basically what you want the metal to diffuse through the carbon fiber sheets or your fabric. Now why low temperature? Because, well, you can also perform this at high temperatures, but this process is typically used when you don't want to go to very high temperatures. So you rather use pressure than temperature, and that is why this is known as low temperature compression. But anyway, if you're okay with higher temperatures and your metal can, then however you need to slowly heat the entire structure, because what you want is you want the metal to melt and slowly diffuse through your structure. Okay, so this is another way of making the laminate type of metal matrix composites. So metal matrix composite, by the way, is a more general term. And when we you can also have other additives, not just carbon. You can have other additives. Then this is a more general term. But when we talk about carbon metal composites, then we typically call them carbon metal composites. But I have not used the term CMC because that may be a little bit confusing. There may be ceramic metal composites. They are also called CMC. So let's just stick with carbon metal composites. Okay, coming to the second type, liquid state processing. So liquid state, the most common liquid state process or manufacturing process for metals is casting. So you melt a metal, you have a cast which is made of a refractory material such as sand, and also for better or more sophisticated molds you can even use graphite. So you have this mold, you fill the metal, it solidifies, then after that you perform the finishing operation. So this is very common. However, what you can now what you can do is you have these chopped fibers mixed inside your metal, and since the volume of these fibers is relatively low, in this particular case you need to ensure that you don't go to very high volumes. But if you take this mixture and then you melt the overall mixture, which will melt at the melting point of the metal, then you can perform casting. You can pour it inside something and then you can solidify your metal. However, there are certain challenges here. So carbon fibers are much lighter in terms of weight. They are much lighter compared to metal. So there is a high probability that they will float. So you may need to stir. So there's something known as stir casting. So slightly stir casting or squeeze casting, you need to make sure that your fibers are uniformly distributed inside your metal matrix when you're performing the casting. Okay. What else? Liquid infiltration. So this is something rather similar to the diffusion bonding that we learned, but the only difference is that now your metal is liquid. You're not using the solid sheets or foils of the metal. So what you do is you pour your molten metal on top of the preformed and you allow it to diffuse and solidify it. Now this can be done at high pressures. Remember that you need to ensure that your metal does not immediately solidify. You may need to control its solidification, and therefore you can play with the pressure parameters a little bit. And this is how you, so this is basically again your molten metal now diffuses through the carbon fiber. The advantage that carbon fiber offers as compared to any other additive is that there is no sort of expansion because of the heat, or there is no adverse effect on the structure of fiber because of the heat. In fact, we know that when we perform heat treatment, carbon fibers always they become better and better and better. So we don't need to worry about what will be the effect of high temperature on the fiber itself. Okay. Now coming to the third one. Third one, as the name suggests, that we are depositing something. What are we depositing? If you remember from the carbon composite class, that we talked about pyrolytic carbon deposition on top of the carbon fibers. So pyrolytic carbon from gaseous hydrocarbons in this particular case. Something very similar, but here you don't have the carbon being deposited, but the metal being deposited on top of your carbon fibers. This can be done using evaporation techniques. These kind of techniques are, so you evaporate a metal at lower pressures or higher temperatures. So these kind of techniques are actually rather common also in the case of microfabrication, evaporation and sputtering techniques. So these kind of techniques often enhanced with plasma, supported with plasma for the, at least a little bit of impregnation of the ions. So this is why it is known as ion plating. So you're doing plating, but you want a very good adhesion. Not impregnation in the in the same way that you do doping or anything. No, that's not your goal. You just want surface plating, but at the same time you want it to ensure that the adhesion is very good and you have nice atomic layers of metals on top of your fibers. And this is what is known as ion plating. You will typically use argon plasma or any inert gas plasma for that matter. Once you have this, now you have the metal deposited on top of your carbon fibers. Now you would like to further process it. So what you can do is you can do hot pressing. So you give it a certain shape. Let's say you wanted to make a hollow cylinder out of this. So you can take one carbon fabric, then you can perform the ion plating, and now you can give it a certain shape. Or if you just want to use the sheet, then you can perform pressing, hot pressing. And if you want to give a shape also, you may need to use the heat a little bit, because you want to go to the not melting point, but the metal should become softer. Okay, only then you can work. So this is also known as this is also certain type of infiltration, because this hot pressing will ensure that your metal now diffuses through or infiltrates through all your carbon fiber strands. Okay. What else? Something again very similar. Using plasma, you can spray the metal on top of your carbon structures, and again you can perform hot pressing or infiltration. Okay, so this was all about the how do we make metal-based carbon composites or metal matrix composites. Applications, as I have already mentioned, there is you can make heat sink, because the property that you require from the heat sink, you require good thermal conductivity but low thermal expansion. So any application that can utilize this property, of course, we can use these materials for that. We can also make the advanced tools or bearings. Again, this is the same property that we are using, low thermal expansion, but good thermal conductivity. So you can make advanced tools which so you basically also improve the tribological properties of your material by adding carbon fiber to it. Okay, we also have other applications, various applications that are related to electrical conductivity. So you can then also do further search. There are various applications where these kind of materials are being used. Here is one article for further reading. However, you can also find many more articles. So yet another very interesting material is carbon reinforced concrete or carbon concrete composite. Okay, so in this particular case, we are also using not just carbon fibers but other types of carbon materials. So in most of the other composites, we were always using fibers. Now you will think that, well, for structural engineering applications, what do you want? You want better mechanical strength in your structures, right? So fibers it should be the first choice. Indeed, fibers are used for reinforcement. However, sometimes you just want to make your concrete stronger. And for that, what you need is filling of the pores of the concrete. And that can be done using carbon nanomaterials. So in this particular case, we are also using carbon particles, although very small, nanoscale particles, or graphene, or even carbon nanotubes. So for carbon, for reinforcement of concrete, you can use carbon nanomaterials. However, fibers still happen to be the first choice for giving the structural strength. We will see how. Okay, so first of all, why do we need carbon reinforced concrete? Well, we always need concrete that is stronger. We always need building structures that are stronger, and if they are lighter, that is very good for us. If you want to make a roof which is lighter, so for that purpose, our carbon materials, they work very well, right? They are strong, but they are lightweight. So that is, of course, one property of carbon materials that we utilize. But there are many more things. Actually, carbon reinforced concretes have become indeed very popular, and there is a lot of work going on. The reason? Well, you can also use it for many other applications. For example, waterproofing. You know that the carbon materials are always hydrophobic. Unless we do certain surface treatment, they typically repel water. So, and also, if you just fill the pores of the concrete, or fill, you can strengthen your material with it, then you have this additional layer of hydrophobic materials. So what you can have is, you can use it for waterproofing. You can also use it for noise reduction, and some other very interesting applications. Fracture detection. How do you detect fracture? You have your carbon materials are electrically conductive, right? If not very high electrical conductivity, at least it will offer some, kilo ohm resistance. So it's reasonable electrical conductivity. Okay. Now what you can do is, when you have a change in the electrical resistivity of your carbon fibers, in that case, you can detect the crack. So you can use these structures also for detection of cracks. Okay. One more thing. Electrical and electromagnetic shielding of the walls, or of the whatever structure, house. Now you must have heard of these smart buildings and intelligent buildings. Actually, if you add carbon fiber to your concrete, that is when it becomes a smart structure. So basically, you add carbon fiber to anything and it becomes a smart structure. That is why I added carbon fiber in this course. So now it becomes a smart course. Okay, so the point is that, well, we can, for all of these smart city, smart housing applications, carbon fibers play a very important role. Okay, now, yeah, what do we do? How do we make these structures? What are the different types of structures that you can have from carbon fiber, and how many different ways you can use carbon-based materials for, as reinforcement? Okay. First of all, how much carbon material should you add? So unlike CFRPs or other carbon-based composites, you will here have much lower volume fractions, because your primary material is concrete. You're using this is just an additive for reinforcement. But if you add too much of carbon material, then your concrete may lose its properties. So you will even use volume fractions as low as 0.5%. So we were talking about 50-60%. Now here we go down to even 0.5 volume percent. So of course 0.5 is more of the lower side. You will have 2%, 3%, 5% also. But of course, compared to other carbon-based composites, this value is pretty low. So you will mostly use the general purpose grade carbon fibers, because you don't really much care for the very high Young's modulus or even very high tensile strength. So you will rather go for general purpose carbon fibers. Okay, so you can mix them into small, as small chopped pieces or as short fibers inside your concrete. That is number one. So here is one picture. These are some structures where they're coated with carbon fiber. So this is how they look like. Okay. Now you can also have non-woven carbon fiber mats. So why would non-woven is after electrospinning, what do you get? Or after melt spinning also, as spun mats are basically known as non-woven mats. So where you are not doing any braiding and you're also not preparing the fabric. Okay. Non-woven mats have randomly oriented fibers, so they actually can be used for electrical shielding of the walls. So for this purpose, so this is, in fact, there are fewer applications where you use non-woven carbon fiber mats. We always want to have, for mechanical strength, weaving is important because we have these perpendicular woven structures, and that is why that provides that sort of distributes the stresses very well. But for electrical shielding, what works better is the non-woven carbon fiber mat. Okay. What you can also do is, rather than using the carbon fiber directly, you can use the CFRP preforms. So we already talked about, also in the case of metal matrix composites, you can use these preforms. And you can not just the preforms, you can also use CFRP sheets or CFRP structures. So laminates, in this particular case, you can use laminates to provide external support to your structure. So here is an image. Let's say this is your pillar, and what you want to do is, now you want to provide external support. So what you can attach CFRP sheets around it. So that is also one option. Okay. What else? So carbon fiber can also be wound. So basically, again, maybe this is clear from the picture here. You have a pillar and you can wind your carbon fiber around it. So these are not individual carbon fibers. These are going to be the ropes of carbon fibers. These are probably going to be thick ropes. So there you have to do, remember from our mechanical property testing lecture, carbon fiber mechanical property testing. So there you need to have a good tensile strength in these fibers. Again, modulus may not be so important. Rather, the ultimate tensile strength, that is more important, and you will most likely choose pan derived or isotropic pitch derived carbon in this particular case, because you don't really want to go for mesophase pitch, because you don't much care for the modulus in this particular case. Tensile strength is more important, and turbostratic nature can also offer a little bit of strain hardening. So you may want to go for these kind of fibers. Okay. Strands of these CFRPs, not necessarily fibers, but also with the resin. So CFRP strands can be used for strengthening cable-like structure. So actually, these kind of cables, carbon reinforced cables, they have been used for a lot of bridge making applications, because here now we are utilizing their load bearing ability. Now we are utilizing mainly their mechanical properties, right? So you can actually make fancy structures. So there are certain some structures have already utilized, there are certain bridges that have already utilized carbon fiber cables or CFRP reinforced concrete cables. But there are also several models, and all these futuristic buildings that we talk about, all these smart buildings and smart bridges, will often have some component of carbon fiber into it, because that makes it lighter, stronger. So in this particular case, for example, this is just a basic drawing, that you can have hollow carbon fiber tubes. Okay, and then you can also further perform the reinforcement with other carbon fiber tubes, and that would make your bridge structure very strong as well as light. Okay. What else? So this is the one that I had mentioned in the beginning already, that you can use carbon nanomaterials that will fill the pores of your concrete and make it stronger. Okay. Now you will typically use pan derived carbons, as I have already explained. Okay. What are the challenges? So of course, the interface properties remain a challenge. So that is true for all kinds of composites. Having the optimum interface properties. Okay, what else? What happens is also the mechanical failure of the structures that are, because you also have not just one type of structure here. You have various different types of carbon concrete composites, right? You have something with, wound wire, and you have also these, sheets. Sometimes these, the CFRP sheets are also used as sandwich structures, not just for the external support, but also as sandwich structures between two different concrete plates, mortar plates. So you can also use, so now what will happen is for each one of them, the mechanical properties are going to be different. So if you have just reinforced your concrete with carbon nanomaterial, the mechanical property of that composite compared to what you have, when you have a sandwich CFRP sheet, the properties are going to be different for each one of them. Different, you need to perform different analyses for understanding their, failure behavior. Okay, what often happens is there are slip planes, slip surfaces developed when you have even slightly poor adhesion, and that can lead to a catastrophic failure of your entire structure. So adhesion is important, yes, but also you need to understand what will be the distribution of loads on your structure. Is your CFRP structure your load bearing structure, or is there, what happens if there is a certain crack in your structure? How much load can the CFRP bear, and where is going to be the slip surface? How is it going to break? So optimization of these mechanical performance and deformation is very important in the case of carbon reinforced concrete. Overall failure of the structure is something that you need to understand. One more issue with carbon fibers, and again this is with a lot of carbon fiber based composites, is the reuse or recycle of the carbon fiber. Once the structure fails, then what do you do with the carbon fibers? This is something that is that you need to think about, because carbon fibers can be to some extent reused, but every time you reuse them, their properties or their value goes very much, it becomes very much lower, because you have brittle carbon fibers, so they may end up breaking a lot when you're trying to remove them from their parent structure and then trying to reuse them. So then you can have a lot of breakage in the case of carbon fibers, and also you may end up losing the little bit of the microstructure of the carbon fibers, also compromised. So you may end up, for example, inducing the voids that then can lead to further cracking. So the recycle of carbon fibers is also one important issue. All in all, now we have discussed a number of carbon-based composites and carbon fibers, and from the next lecture onwards, we will be talking about carbon nanomaterials.